In this example, we're going to expand out some power series just to a few terms. We're going to use the first several terms to see what the graph looks like, because all of these should be a function that we know very well, and then we're going to determine what that function is. So I'm going to write out, let's say, the first 10 or so terms for this series. So when n is equal to 0, I'm going to plug 0 in for n. I would have negative 1 to the 0, x to the 0 divided by 0 factorial. Remember that 0 factorial is defined as 1, and anything to the 0 power is equal to 1, so that first term is just 1. Now I'm going to go on to when n is equal to 1, so I would have negative 1 to the first power, x to the first divided by 1 factorial, and so that's just a minus x. And hopefully you'll start to see a pattern in here, because when n comes out to be an even number, we're going to be having negative 1 to an even power, which is going to give us a positive 1. So here I'll be adding x squared over 2 factorial. And when n is equal to an odd number, like negative 3, we have negative 1 to an odd power, which is going to give us a negative term for all of the x's that have an odd power with an odd factorial in the denominator. So I'm just going to use that pattern to write out the next few terms. And do make sure that you put a dot 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 on the end, because these are series. They do not end. They're infinite series. And now I'm going to pull over a graph. I went and I graphed this function. So I graphed the first several terms. So you can see in my y, and I could have done this on a calculator too. Sorry about that. Because we can put factorials in the calculator, but notice I am changing my signs negative positive. So this is what the graph looks like, and we're interested in what's happening near 0. So I'm going to zoom in closer to 0, and what we're being told here is that this graph here, close to x is equal to 0, should be very similar to a graph that we are familiar with. Well, one thing I will point out is that notice that earlier, when we talked about the power series for e to the x, it was almost the same as what we have, just that this here, the power series for e to the x, does not have the negative 1 that we have here. So that hopefully does ring some bells. And then even just looking at this graph looks a lot like the graph of e to the x, but it's reflected over the y-axis. So I'm going to stick a negative in front of the x, and look at how perfectly those line up. Both of those functions are still on, we just can't see they're right on top of each other. And that is because this power series represents the function e to the x. So we can see where the approximation starts to not be so good here, because this still is an approximation at this point, right? Because I only stopped at 10, but I could have gone on. I can keep going all day. The more I go, look, you see how much better the approximation got with me just adding on that x to the 11th power. When I take it off, the approximation stops being good somewhere between 3 and 4. But when I put it back on, the approximation is a lot better, almost all the way out to 4. So that's our first example of looking at power series and writing out a few of their terms. So now let's go on and look at example B. So we're going to start off the same. I never really finished the first example. I guess I will put here, what is the function? Y is equal to e to the negative x. And we looked at the graph of that. Here I will start by writing out some of the terms. The first term is going to be positive. We're going to have x to the 0 over 0 factorial. That's just a 1. When n is equal to 1, our term will be negative. We'll have x squared over 2 factorial. When n is equal to 2, our term will be positive. We will have x to the 4th over 4 factorial. So I'm just going to write out a few of the terms for this series, and then I'm going to do the same thing. I'm going to go over and graph this. Notice that all of these exponents are even because of that 2n that's in the numerator. And the ones that are even by doing 2 times an even number are positive, and the ones that are even by doing 2 times an odd number are negative. So I'm going to go to Desmos and graph these and see what we see. So I have gone up to the x to the 10th power. This is what the graph looks like. We are again interested in what's happening at 0. So I'm looking at this right here, this area here, and hopefully that, even the big picture, kind of looks like the graph of cosine. All with this hills and valleys, the sinusoidal activity going on. And then I'm going to go a little bit further and graph x to the 12th over 12 factorial. And then I'm also now going to graph the function cosine and look at what we see here. The green graph matches up perfectly with the red graph until about somewhere between 4 and 5. And if we were to go on and add on another term, we can see that the approximation becomes more accurate further away from the center of 0. So this function represents y is equal to cosine x. So in the next few examples, I'm not going to work through these. I would like for you all to work through them. Write out the first several terms, graph them, and see if you can figure out what graph it is. And when you're trying to figure out what graph it is, you should be looking only close to 0. One of them is a trig graph. One of them is a trig inverse graph. And the third one's a little bit tricky. But keep in mind, though, this isn't something that you would be like quizzed or tested on. These examples are more so to give you an idea of what it is that a power series is. And remember that we're not graphing power series. We're still only graphing approximations because this ended, and we know that in reality, these are infinite series and it would never end.